Yeah, it's very good. That's perfect. Hello, and welcome back to our discovery track. And it is my pleasure to welcome Marvin Waldman, Senior Research Fellow at Simulations Plus. And Marvin will be talking to us about modeling Tautomer preference. Marvin, the floor is yours.
Thank you. So this is a poster, actually. It's the first time I've ever done a virtual poster. So I'll be focusing in on various parts of the poster, a little bit different from the usual slide presentation. So this is going to be a talk about a new approach to predicting the preferred or dominant tautomer of a molecule based on a machine learning model. Let's focus in now. So as you probably know, many drug molecules exhibit multiple tautomeric forms based on our internal data sets of drug or drug-like molecules. We find about 30% of them exhibit tautomerism. And the tautomeric state of a molecule affects almost all of its properties: log P, solubility, permeability. Consequently, choice of the tautomeric state will affect the results of building machine learning models, QSAR models. The choice of the tautomer affects the descriptors, typically that you input to the model. The choice of the tautomer will affect the predictions of a model. So as a result of that, you'll find in the literature a number of role-based or scoring methods have been developed to try to standardize molecules into a standard or canonical tautomer. And what's usually desired is that standardized tautomer generally be the preferred tautomer in aqueous solution. But it's been found that these scoring methods, typically based on fragments or counts of fragments or scores assigned to chemical fragments, ketones versus enols, and so on, they have limitations in how well they work, because in actuality, the preferred tautomer in solution is often the result of a complicated interplay of multiple factors, which is hard to capture with simple scoring rules. So we decided to try out a project where we're going to use our capabilities of ADMET Predictor and ADMET Modeler to build an artificial neural network ensemble machine learning model that would predict the preferred tautomer, ideally in aqueous solution. The goal was to obtain a model that was both accurate and fast to run. It could be used to standardize tautomers or rank candidate tautomers. So not only do you get potentially just one tautomer out, but by ranking, you can choose the top 2 or 3 tautomers, for example, in docking applications. So the way we went about this, in ADMET Predictor 10.3, we released the first version of this model, which was based on a collection of about 200 molecules, which we already had in use because we already had a rule-based approach. And that rule-based approach was based on tautomer preferences from drugs or drug-like molecules across about 200. But recently, a publication appeared in the literature in 2020 called Tautobase, where they provided a database of tautomer preferences based on a manuscript that had been written by Peter Taylor and Peter Kenny, who provided many, many examples from the literature. And the Tautobase article collected this into a database. So we used, and that was a publicly accessible database, so we downloaded that. We did various curation exercises on it. We removed examples from non-aqueous solution, from gas phase. We excluded examples where the tautomer pair preferences showed only a weak preference for the dominant tautomer, i.e. the log of the KT equilibrium constant was less than or equal to 0.1. We removed duplicates. We went back to the original literature for all these examples and reconsulted them and corrected a number of structural errors. In the end, we settled on a database of 1,529 molecules, 200 of which came from our internal collection originally. 1127 came from Tautobase, and another 200 resulted from additional examples we found in the process of this curation when we consulted the original literature. Then we used ADMET Predictor to take each one of these preferred tautomers and generate additional tautomers for them. Admit predictor has an ability to generate or enumerate tautomers. So we did that for all of these 1529, and that exploded out the total data set to a total of 7,251 tautomers, of which 1529 were marked as preferred. So in this example, I'm showing a scaffold that you find in the acyclovir molecule. And we exploded that out. So the first one is the preferred tautomer marked with a 1, and the others are marked with a 0. So that's basically the endpoint that we're trying to model here. We then used Admit Predictor to generate descriptors for all of these tautomers. And then we removed all descriptors that were tautomer independent. So we were only left with descriptors that change as a result of the tautomer. So things like number of carbons, number of fluorines, number of total rings, and so on were all removed because they're independent of tautomer. So they really can't be used to tell you which tautomer to prefer over any other. But we were left with about 200 descriptors remained after we did that, such as E states, functional groups, keto versus enol, counts of aromatic, aliphatic, anti-aromatic rings, counts of dipole-dipole or lone pair repulsions, various descriptors that depend on our partial charge model, internal hydrogen bonds. I highlighted these 3 in blue because these were ones that were added from our original descriptor set based on the Taylor-Kenny manuscript as factors that have a strong influence on tautomer preference. And we also expanded the internal hydrogen bond descriptor to include examples that we previously weren't accounting for that were pointed out by Taylor and Kenny. We then removed descriptors that using our usual procedure. We've removed low variance and correlated descriptors. We performed sensitivity analysis to rank the descriptors. We partitioned the data set into a training and test set. In this case, we did it slightly differently from the usual approach in that all the tautomers of a given molecule were exclusively assigned to either the training set or the test set. There was no separation of tautomers from the same molecule, some of them going to training or test. So we did this by first partitioning just the dominant tautomers and then assigning all the tautomers associated with the dominant tautomers of the test set, taking all of their accompanying tautomers and also adding them to the test set. We then built a grid again of artificial neural network ensemble models where we varied the number of inputs as usual, and then we varied the number of neurons. So this gives us a grid of models to select from. And we did a few things here that are a little bit different, again, than our usual protocol in Admit Modeler. Some special changes had to be made to build this model. So here I'm showing a typical depiction. Pankaj showed us something similar earlier of a typical neural network architecture, set of descriptors multiplied by weights, which feed into the hidden layer of neurons. Sigmoidal transformation is applied there, and then another set of weights is applied to produce the output prediction. This is a typical architecture for a regression model. In the case of the Tautomer model, we applied a further transformation based on a softmax transformation. So this gives you an output which varies now from 0 to 1. The denominator here in this softmax transformation is a little bit different. The sum is over all tautomers of a given molecule. So the idea here is that you want this sigma value to be as large as possible for the dominant tautomer and to be smaller for all the non-dominant tautomers. This was fed into a cross entropy loss as the objective function. You can find this discussed in the literature, but with a bit of a tweak here, where this sum is performed over the preferred tautomers only. The reason being that these labels across all the rows are not independent. So only one tautomer of the collection is marked with the 1. So if I were to flip one of these to a 1, this would flip the preferred tautomer here to a 0. So part of that was to address that by summing over the preferred tautomers. It also reduces the effect of imbalance, as there are many more non-dominant tautomers compared to dominant tautomers. And also it tends to equally weight the tautomers of the molecules the same. That is to say, it equally weights each molecule. So if one molecule has only 2 tautomers and another molecule, in some examples, has over 100 tautomers, those 2 molecules weight equally rather than giving a lot of weight to the molecule with, let's say, 100 tautomers versus 2. So this is done 165 times using Admit Modeler. We train 165 networks. We select the best 33. We average the scores over those best 33 networks, and the score with the tautomer having the highest score is classified as the preferred tautomer. So we do this over this grid of architectures representing numbers of neurons by numbers of descriptors. And we select the best overall ensemble model that produce the overall fewest false negatives and positives for the training and the test sets. And this results in an ensemble of 33 artificial neural networks. And this here I'm depicting the final model performance. Across the 1,529 molecules and 7,251 tautomers, we wound up with 142 false negatives or 142 false positives. Again, because we only mark one tautomer out of a collection as being the dominant tautomer, each false negative results in one false positive as well. So the false negatives and false positives in this approach wind up being the same in terms of the total number. So this model can now be used to score tautomers. So here I'm taking a cyclovir and using our generate tautomers approach. We generate multiple tautomers of a cyclovir, we score them. So this can now be used to rank tautomers as well as standardize them. To get an idea of how much we've improved on this result, we can use our tautomer standardization protocol. Now we've added a new option here. This actually occurred in 10.3 with the previous tautomer model. So you can standardize tautomers using the old rule-based approach or with the model-based approach. You also have 2 ways of enumerating the tautomers for selecting out of the enumerated tautomers which one is the best. And you can also customize this. I don't have time to go into this, but you can add your own set of queries that mark certain patterns as being preferred over others. We provide a default set for this, but users can add to this or modify it, so they can override both the rules and the model with their own choices in various cases. But anyway, so if you count 2 times 2 times 2 here, there's 8 different ways of doing this. And so I show the results of that on the original 1,529 molecules, and it generated, using the old rule-based approach, it transformed what would have been 1,529 correct results, changed varying 318 to 397 of them. So these basically, the more you get here, the more wrong you are. These are essentially false transforms. But when we use the model-based approach, it only changed, varying again from about 119 to 145. And the model-based approach runs in about 5 seconds on an 8-core i7 laptop. So it is very fast, and you can see it's more than twice as accurate as the previous rule-based approach. So the conclusion, we built a machine learning model capable of accurately selecting the preferred or dominant tautomer among a series of candidates. Its accuracy outperforms our previous rule-based approach by better than a factor of 2 on over 1,500 examples, and it can be used to standardize tautomers for building QSAR models and other cheminformatics applications such as docking or database registration. And I don't have time for acknowledgments, but everybody that was mentioned previously is acknowledged as well they all contribute, especially David and Bob Clark, our former senior research fellow as well.
Right.
And
Great.
thank you.
Thank you, Marvin, for all this information. Very, very interesting. I'm just going to launch the poll on the particular relevance of tautomer handling for our client's current line of work. And I'm going to leave that up essentially to the end of the session, because I think we've got about 10 seconds left. And then we will jump onto the discussion panel. So thanks to everyone for their contribution, and we look forward to seeing you in the discussion panel. Bye-bye.